oscillating in a vertical plane about a horizontal axis passing through the point O. The vertical plane in the diagram I have denoted it as XY. As I already told you, O is the point of suspension, C is the center of mass, and the mass of the compound pendulum, let me take it as M, and the moment of inertia about the axis of oscillation or rotation, I will call it as I. I repeat once again, I am taking the mass of the pendulum as M, its center of mass is C, and moment of inertia about the axis of rotation as I. The length of the pendulum, let me take it as L. For those of my friends who have not listened to me carefully, I am repeating them for their sake. O is the point through which the axis of rotation is passing. M is the mass of the compound pendulum. I is the moment of inertia about the axis of rotation. L is the length of the pendulum. If the pendulum is displaced, let it be displaced by an angle theta, so that when it gets deflected, it starts to oscillate and executes SHM, simple harmonic motion. As we proceeded in the previous case, we need to first write what is the kinetic energy. The kinetic energy, as I said, is denoted by the letter T. It is half I theta square, theta dot square. Am I right? Theta dot square. Here the oscillation is about an axis, moment of inertia about the axis of rotation is I, and therefore kinetic energy has to be given in terms of moment of inertia, and therefore I have taken it as half I theta dot square. Let me call this as equation number 1, sir. The potential energy, again it is mgh, again it is mg into L minus L cos theta. Is that okay to you, sir? If I take this L outside, I can as well write 1 minus cos theta. Let me call this as equation number 2, sir. Now we have to write the Lagrangian for the system. The Lagrangian for this system. L is equal to T minus V. Therefore, L is equal to half I theta dot squared minus mgl into 1 minus cos theta. Is that okay to you, sir? Let us call this as equation number 3. Okay, that is equation 3 for us. And we have to write the Lagrangian equation for this system. For our system, the Lagrangian equation, d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. Is that okay to you, sir? I will call this as equation number 4, sir. Now from 3 I can find out dou L by dou theta will give me half I 2 theta dot. Therefore, this will be I theta dot. Similarly, dou L by dou theta will be minus MGL sin theta. I don't think you will have any difficulty whatsoever in following this because we have done that in detail in the previous application, simple pendulum. So for all that I need to do is substitute d by dt of I theta minus of minus plus mgl sin theta is equal to 0. This will give me I double dot plus mgl sin theta is equal to 0. This can further be written as theta double dot plus mgl upon I into sin theta is equal to 0. As I already told you, if the amplitude of displacement is small, if amplitude is small, then theta double dot plus mgl upon I into theta is equal to 0. That is the equation of motion for a compound pendulum whose time period is given as t is equal to 2 pi under root of I by mg. Is that okay to you, sir? So potential energy, kinetic energy, you write the Lagrangian, L is equal to T minus V, substitute, write the equation for Lagrangian equation for this system, find out the values of dou L by dou theta, dou L by dou T, substitute, finally you arrive at the expression for the equation of motion of a compound pendulum using Lagrangian equation. If this is clear to you, I will rub this off to go into the next topic for discussion, which is Atwood's machine. Let me first draw the diagram for this. Mind you, this is a pulley. Small m1, the mass attached here is small m2, and if I take this as reference, from the reference we can take potential in at this point 0. If the length of the thread or a string which passes through the pulley is L, and this is X, okay. This will be L minus X from here, okay? And I will call this as A, and let us say it that point, let me take it as Q. Before we start with any application, we need to go with the assumptions first. What are the assumptions we are making here? The first assumption I am making is pulley is massless, frictionless. Pulley, I will write here. The assumptions are pulley is massless, frictionless. The string is inextensible and massless. These are the two very important assumptions we make. A setup where you have a pulley, an inextensible string is passing the pulley, and two masses M1 and M2 are attached to the ends of the string. Such a setup, you call it as an Atwood's machine. Let us go into the diagram and see what the diagram tells us. PQ, you can see there in the diagram, PQ is a string passing through the pulley, which is frictionless, massless, and the pulley I have denoted it as A. So PQ is a string passing through a pulley A. Both the ends of the string are attached to masses M1 and M2 respectively. I am not writing all these things on the board. I am telling this once again so that you can make notes. Let PQ be an inextensible massless string passing to a pulley, frictionless pulley A. To the ends of the string are connected masses or attached masses M1 and M2 respectively. The length of the string between M1 and M2 is L. The length of the string between P and Q or M1 and M2 is L. And from the diagram, it is obvious that between PA, the length is X. Between QA, it is L minus X. And here I consider X as an only independent coordinate. X is the only independent coordinate. Is that okay to you, sir? So we proceed. The kinetic energy of mass M1, this will be half M1 x dot square. I suppose you will not have any doubt in understanding why I have written half M1 x dot square. Similarly, the kinetic energy of mass M2 is half M2 x dot square. If I add these, I will get the total energy of the system. Total kinetic energy of the system. I write this as equal to T is equal to half M1 plus M2 into x dot square. You need to write the potential energy of both the masses. The potential energy of both the masses. What do I write? V is equal to minus mgx minus past the y I have written minus x. I have taken this as reference line. At the reference line, I have taken potential energy as 0. Anything above this reference line, potential energy must be positive. Anything below this reference line, the potential energy is negative. X is below this reference line, so minus mgx. L minus x below this reference line, minus mg L minus x. Is that okay to you? Following the same steps, the Lagrangian of the system. This is L is equal to T minus V. Therefore, I write L is equal to half m1 plus m2 into x dot squared minus mg. There is a minus, therefore plus mg x plus mg L minus x. That is the Lagrangian of the system. For our system, Lagrangian equation. d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. Okay. We can find out dou L by dou x dot. This will give me half m1 plus m2 into x dot. 2x dot, am I right? 2x dot. 2 will go off to give me m1 plus m2 into x dot. Similarly, I have to find out dou L by dou x. That will be mg minus, this must be m1g, m2g, therefore m1g minus m2g. Finish. Is that okay? Therefore, can be written as m1 minus m2 into g. m1 minus m2 into g.